Okay, let's start with just a little bit of review. Series circuit is when everything is connected one after the other. And to find the equivalent resistance, all you do is add the individual resistors. Okay. When we look at a parallel circuit like this one, okay, the current splits when the wire branches, and part of the current will flow through one resistor and part of the current will flow through the other resistor. It's not always even, though. In this case, the resistors have the same resistance, so it is the same. To find the equivalent resistance for resistors connected in parallel, this is the relationship you use. 1 over Req equals 1 over R1 plus 1 over R2, etc., etc. Okay. All right. Now, let's say I had these two little tubes connected to together. Are they connected in series or parallel? They are connected in parallel. Okay, just like electric resistors would be. Now, both of these are being fed the same pressure. This is like being fed the same voltage. Okay, so they're going to have the same pressure driving them through. Which one of these is going to have the greater flow rate of water going through them? Okay, well, the one that's got a little bit wider is going to have more flowing through it. Okay, this is like the 4 ohm resistor. The 4 ohm resistor has less resistance. All right, so there's going to be a greater amount of current flowing through the 4 ohm than there is the 8 ohm. And here some work magically appears. So what is the equivalent resistance? 1 over 4 plus 1 over 8 equals 1 over Req. Req equals 2.7 rounded. Okay, what is the current exiting the battery? So what we do is we use our equivalent resistance, okay, and V equals IR again. V equals IR is a powerful tool in this unit. You'll use it extensively. So V is 9 because that's the voltage of a battery. Our equivalent resistance is 2.67 or 2.7. Okay, and our current exiting the battery is 3.37 amps. What is the current flowing through each resistor? Okay, so this is maybe where it might be a little weird, maybe not. Okay, everything on this side of the battery is 9 volts. Everything on this side of the battery is 0 volts. So there's 9 volts across both of these resistors. Okay, so to find the current flowing through this 4 ohm resistor, we use the voltage drop, which is 9 volts, and V equals IR. Okay, so 9 equals current times 4 the resistance, and we get the current is equal to 2.25. Okay, and we'll do the same thing. Now this resistor here has the same voltage drop, which is 9 volts. So we use the same 9 volts. The only thing that's different is we use 8 for the resistance, and we get that the current is equal to 1.13. Now something's interesting to note, if we add these up, okay, if I add up the current flowing through this resistor and the current flowing through this resistor, I get 3.38, okay, which is surprisingly close to this 3.37, perhaps just a little bit of rounding error. Okay, and that is the case. These the current exiting I1, okay, I1 here is 3.37. Okay, that's equal to these two currents. They have to split off. The current's got to go somewhere. Some of that 3.37 goes this way. Some of that 3.37 goes that way. Okay, so here I've rounded my answers a little bit more just to make them a little more palatable. So again, I've got 3.4. If I add these up, I get 3.4, and that's equal to the 3.4 that's feeding them. Okay, so they add up to be the same, and that will always be the case in a parallel circuit. Okay, the sum of the currents going into a little joint equals the sum of the current going out of the joint. Okay, all right. What would the current be over here? Okay. Remember, the current entering the battery is the same as the current exiting the battery, so it would also be 3.34 amps. Okay. Now, what would happen to the voltage drop? Okay, what would happen if I add another 12 ohm resistor in parallel? Okay, just kind of thinking through this. Okay, these are the kind of questions I'm going to ask you on the test, so follow along. So if I add another 12 ohm resistor in parallel, what's going to happen to the voltage drop across these? Well, nothing. Okay, I still have 9 volts on this side and 0 volts on this side. So that doesn't change the voltage drop across these. What happens to the equivalent resistance? What I say happens to the resistance of a parallel circuit when you add another resistor in parallel. It always goes down. Okay, so the equivalent resistance is going to go down. So if the equivalent resistance goes down, what's going to happen to the current exiting the battery? Okay, well, if there's less resistance, I'm going to get more current flow. Okay, the current through these branches is going to be completely unaffected. Okay, well, yes. Okay, it's going to be completely unaffected. The only thing that's different is I'm going to get some more current flowing through this branch. Okay, and the current coming out of the battery is going to have to make up for that. Okay, now will the equivalent resistance be more or less than 30? Okay, of this circuit. Okay, well, it's going to be less than 30. Will it be more or less than 10? Okay, maybe it's between 10 and 30? No, it's less than 10. Okay. If I have a 10 ohm resistor and I add another 30 ohm in parallel, the resistance goes down of the total circuit. Okay, so the actual equivalent resistance would be 7.5. Okay, so here is a picture of the circuit, kind of in 3D in picture form. Notice we've got the battery pumping up. Okay, we've got fewer, in this case, protons flowing through the 30 ohm resistor than we do the 10 ohm resistor. We've got, we should have exactly, do we have 3 times as many? I think so. Okay, 3 times as many electrons flowing through the 10 ohm resistor than we do the 30 ohm resistor. Okay, notice that they come back together. Okay, and all the current is the same. So this is the current is all the same until it splits. Okay, how does the brightness change if another bulb is added in parallel? Well, with an ideal battery, okay, let's look. So here I've got 9 volts on one side of the battery and 0 volts on the other. Okay, here I've got 9 volts on this side of the battery and 0 on the other. I'm going to have the same current going through the light bulb. I'm also going to have the same voltage drop. Okay, so the brightness of the bulb isn't going to change. Okay, if you add another one in parallel. Okay, now what did change is the resistance of my equivalent circuit. Okay, so if my equivalent resistance goes down by a factor of 1/2, if V equals IR tells me I'm going to get twice the current, and the battery is going to drain twice as fast. Okay, that's the only thing that's different. Okay, the battery drains twice as fast. Now, what if one of these light bulbs burns out? What happens to the other one? Okay. Well, does the other one stay lit, or does it go out too? It'll stay lit. Okay, because we still have a complete circuit going through that light bulb, so it'll stay lit. Okay, so how do you wire the headlights of your car? Do you wire them in series or parallel? That would not be a good thing if when one of your light bulbs burned out, the other one went out too. That would not be. That would kind of eliminate the redundancy of having to. So they're definitely wired in parallel. Okay. So let's say we've got a lamp with a resistance of 360 ohms and one with 144 ohms. They're connected in parallel to a 120 volt circuit. Which burns brighter? Okay. So first of all, which do you think is going to burn brighter? The one with the greater the resistance, or the one with the lower resistance in parallel? Okay. It's key that you always got to think, am I thinking parallel or am I thinking series? kind of a tough question right now. So let's just go ahead and calculate them. So here we've got 120 volts. Here's my 360. Here's my 144. Okay. So V equals IR. We get 0.33 amps. Okay. P equals IV. We get 40 watts. Okay. Do the same on the other side. V equals IR. 120 volts. 120 volts across. Okay. I times 1. V equals IR. I equals 0.833 amps. Okay. P equals IV. Okay, I equals 0.833, and 120 is my voltage, and we get 100 watts. Okay, so the one that burns brighter here is the one with the lower resistance. Now this is the opposite of what happened when we dealt with things in a in the series situation. In a series situation, the lamp with the greater resistance burned brighter, and that's because it took the lion's share of the voltage. Okay. In this situation, they both get fed the same voltage, and the one with less resistance is going to get more current. Okay, let that sink in for a second. So they have the same voltage. The one with less resistance is going to get more current. Therefore, P equals IV is going to have the greater power. Okay. This is what your electrical outlets would look like if they were connected in series. Okay. This is not how they're connected. Okay. This is how your electrical outlets in your house are connected, and they're connected in parallel for a very good reason. One, you would not like it if your fridge shut down because you turned your the light switch off. Okay, that would not be a good situation. So you want everything to stay running, which means you want it in parallel. Okay, so let's say we've got a circuit breaker, 15 amps. Right now everything is fine. We've got a 7 amp microwave and a 7 amp fridge running, or 8 amp microwave. And here we've got an unused outlet. Okay, these are the prongs of those outlets, and when you plug something in, you connect the resistance to that branch of the ladder, and you cause more current to flow. Okay, now when these are set to only handle a certain amount of current, a certain amount of breakage, typically it's a 15 or 20 amp circuit is what you guys run, depending on if you use 12 gauge or 14 gauge wire. So if that'll pop, now that'll pop the power to all of these, okay, and the whole circuit goes out. So this is one circuit, and these are various outlets, okay. Okay, I would normally do this as a demonstration, but since we're doing this on video, I'm just going to tell you the answers. So which burns brighter? The first lamp, so here we've got 2 light bulbs connected in parallel. Okay, so I've got 200 watt light bulbs, one after the other. Which is going to be brighter, the first one or the second one? Okay, it will be the same. Okay, it doesn't matter. There's really no first or second in parallel. Okay, so all right, what happens if you remove one light bulb? Does the other one stay lit in parallel? Yes. Okay. With a 100 watt light bulb and a 40 watt light bulb, which burns brighter? Okay, in parallel. So if I just, from what we just went over, the 100 watt light bulb is going to have less resistance than the 40 watt light bulb. Okay, which means that's why in parallel, which is how these light bulbs are designed to work, okay, the 100 watt light bulb is brighter. Okay, all right. Now in series, okay. So which bulb burns brighter, the first one or the second one? If they're both 100 watt light bulbs, okay, they're both the same. What happens to the other light bulb when you remove one of the light bulbs? If it's in series, then the other light bulb goes out. Okay. With a 100 watt light bulb and a 40 watt light bulb connected in series, which one burns brighter? Well, the opposite actually happens when you connect them in series. The 40 watt light bulb, which has the greater resistance, burns brighter than the 100-watt light bulb, which has a lower resistance, because the 40-watt takes more of the voltage, and they have the same current. Okay, they have the same current. Okay. In series with multiple resistors, there's a 60 ohm resistor. So we've got a series circuit with multiple resistors. Okay, is the equivalent resistance compare? Is the equivalent resistance be more, less, or the same as 60? So we've got multiple resistors connected in series. One of them is 60. Is the equivalent resistance more or less the same than 60? Think about it. Okay, it's going to be more. Okay, whenever you add any resistors in series, the resistance always goes up. Okay, if a 100 ohm resistor is added in series, then the equivalent will be more or less or the same. Okay, it will go up. Okay, now when I add that 100 ohm resistor, what happens to the equivalent resistance, the current, and the voltage drop of each resistor? Okay, when I add a 100 ohm resistor in series, the equivalent resistance goes up, okay, which is going to cause the current to go down, okay, and that's going to cause the voltage drop across each of the resistors to go down as well, because they don't have as much current flowing through them. Or the other way to think about it is that 60 ohm resistor is taking some of the voltage. So that 100 ohm resistor, sorry, it's taking some of the voltage, which is shared among the resistors in series. Okay. In a parallel circuit with multiple resistors, okay, there's a 60 ohm resistor in it. Is the equivalent resistance compare B? Okay. Is the equivalent resistance more or less the same as 60? It's going to be in parallel. It's always going to be less. Okay. If a 100 ohm resistor is added, let's say let's make that say parallel. If a 100 ohm resistor is added in parallel, then the equivalent resistance will I need to work on this slide. Will the equivalent resistance be more or less the same? If I add a 100 ohm resistor in parallel, the resistance is going to go down. Okay. So what happens to the equivalent resistance? We just answered that question. The equivalent resistance goes down. Okay. The current, if the resistance goes down, the current's going to go up. Okay. What's going to happen to the voltage drop of each in parallel? Now you got to have the picture in your mind of the parallel situation to answer this properly. The answer is the voltage won't change, okay, because they each get fed the voltage. Alright, we're going to skip this for now. Okay. Alright, that's it for today. I know that was chewy. Hopefully that made some sense to you guys. If not, Google a little bit of Khan Academy maybe, or something along those lines, and see if they can explain things to you in a different way. Alright, good luck.